Okay, this is the kinetic. Theory of reaction rates. This is divided into really two theories in itself. Uh, One we call the collision theory, and the transition state theory. Now, the uniqueness of this concept is that when we take into account the collision theory, we're talking about a micro level analysis. That is, particle behavior and particle functions, characteristics. And when we talk about the rate laws in terms of concentration factors, we're talking about a macro level concept in which we just change and look to change the um, concentration and look at change in rate without taking into account, well, what are the particles doing in the process? So one's macromolecular and one's micromolecular. This is the micromolecular description. Now, the micro level description mathematically is based upon probability and statistics. And we're not going to get into the statistical mechanics that go with this, but you will understand when I talk about the what we call the rate distributions or particle velocity distributions in there. We're taking averages and what we call a Maxwell-Boltzmann distribution curve. Okay, so when we talk about the collision theory, we need to look at what we call a probability distribution of particle energies or particle velocities. And this is called the Maxwell-Boltzmann distribution curve. Or just the Maxwell-Boltzmann curve. And what you'll find is it'll have it's dependent on temperature. Its shape is dependent on temperature. So at one temperature, say T1, it will have this shape. And what it's showing is particle energies increasing and decreasing, particle energies increasing from left to right. And over here, we'll put this little sigma Greek letter, and that represents particle numbers. Well, at, say, room temperature, this room is at 25 degrees roughly Celsius. Well, let's say we find that some particles in this room have low speeds and low energies. That's also velocity. And some of them have high speeds and high energies. Okay? But we find that the majority of them are found right here at this high peak in this curve. And this is called the root mean value for the energies or root mean square speed. V bar. Well, V bar is root mean or the average speed of all the particles in this at this temperature. And you could calculate that root mean using this simple formula, 1/50th square root of T in Kelvin temperatures over the mass, atomic mass of whatever particle, molecular mass, and just a molecule. Using this expression right here, it's a very simple equation, 158, and it gives you those speeds in meters per second. show you some others in them shortly. Now, if you heat the particles, I'll use a different color, you'll find that particles will shift to the right in terms of their velocities and energies. And so we will see the curve change by shifting a lot of the particles to the right now, and then we'll have T2 being greater than T1. And now, we need to continue to heat particles and get a significant number over to the right side, say T3. Well, what's unique about this is that you can use this curve to define what is known as activation energy for a reaction. Particles of a reaction have to be at or above this energy threshold or velocity threshold in order to proceed to products, and that's called the activation energy, delta EA, activation energy. And stating that in another way, if the particles on the left side of that green line have energies, they don't react. You have to be at the green line or higher in energy. So particles must be at or above the activation energy when we talk about a chemical reaction. Now, I've tried over the years to find acronyms to help students remember these things. And so for this one, I have a simple acronym, and you just kind of have to remember the last two letters, I guess, P, A, M, V, C is the acronym for the postulates of the KM theory. P stands for particles, attraction, repulsion, movement, I'll explain that, velocity, and collision. When you look them up online or in a book, you may not find them specifically in this order, but it fits my acronym, PAMVC, PAMVC, whatever. All matter is made up of particles, either molecules or elements. So that's where the P comes from, particles come from. All particles interact by either attraction or repulsive forces. All particles at and above absolute zero, Kelvin zero, are in constant motion. Three modes of motion: translation, rotation, vibration. And velocity of the particles is directly proportional to the kinetic energy content. That is, if you heat particles, they move faster. If you cool them, they move slower. So you put proportional to kinetic energy. Content. And that's where we apply that concept to get the root mean square speeds, statistical speed of particles at a given temperature. I showed you that little equation a minute ago. And the collisions between particles are considered to be perfectly elastic. And what that means is the sum of all the energy changes is equal to zero for the collisions. When the particles collide, there is a heat loss, but it also reabsorbs that heat in terms of electromagnetic radiation, light, and it balances off to zero. But in the KM theory, it's just neglected and said to be zero energy change when the particles bounce into each other. And so we use these to define certain behavior on the molecular level of how particles behave. Now, how does this apply to the Km theory? How does it apply to the Boltzmann distribution? On a molecular level, when a reaction occurs, reactants go to products. If the following occur simultaneously. Now, don't get this mixed up with the rate factors that you can't see, but I use an acronym here, CENT. So these are reaction factors, not rate factors. Can't see as a rate factor. Reaction factors is CENT. And this stands for what we call concentration, which is a kinetic concentration, effective collisions, nature, naturally reacting particles, and proper temperature, reaction temperature. When we talk about proper kinetic concentration, we're talking about the ability of components to find each other. If you have a reaction A plus B goes to products, of course A must find B. So if I had one particle of A in one end of the room here and B in the other, it's not a big probability that they're going to find each other. But if I fill up the room with a lot of A's and B's, I would have what we call an effective or proper kinetic concentration. And so the particles would be able to find one another easier. When we talk about effective collisions, molecules interact by collision. Well, not all collisions result in bonding. So because of the geometry of the molecules, sometimes they bump into one another, but they're not in such an orientation that they connect. But sometimes they do, and they hook together. And that's called the proper collision or effective collision. And this has to do with orientation during the collision. And of course, it stands to reason without a lot of analysis that you have to have particles that will connect and bond. Pluses hook up with minuses, and so if you throw in a couple of positives, there's not a lot of probability of it reacting. Now there are metals that interact with metals, so there are exceptions to everything, but you have to have reacting particles. And finally, you have to be at or above that activation energy. So this is the delta EA. If you're not at or above the activation energy, you're not going to have any reaction anyway. Now, when I say simultaneously, that's the importance of activation energy. These four items come together simultaneously, you get products. That's what the kinetic molecular theory predicts. And so the probability is these factors, concentration, effective collision, naturally occurring product, all go into a probability expression known as the Arrhenius equation. This predicts the rate of reaction as a function of temperature. That is K is proportional to E to the minus delta E over RT is the expression, where that's the activation energy here. Well, what I could do, instead of messing up the note, delta EA is equal to the activation energy R is the gas constant, thermodynamic form. T is Kelvin temperature. And K is rate constant. Now, a specialty equation evolves out of this, called the Arrhenius equation also, where this is set equal to K equal to E to the minus delta E over KT by inserting a proportionality constant. And then solving for A, and you have A1 equal A2, or two different temperatures, is what it ultimately refers to. Like that. And so you have temperature 1, temperature 2. That's temperature I. I'll just put a subscript I there. And you can apply 1 and 2. Where A1 equals A2, then you take all of the stuff on the right and turn it into an equation. And this is the Arrhenius equation. And this is all you have to learn. You're not going to have to derive the thing on a test or anything. So it's K2 over rate constant 1 is equal to delta E over A over R, thermodynamic constant, times T2 minus T1 over T1 times T2. You must learn that. I don't give it to you on test day, but you will have problems that you will have to work using the Arrhenius equation. We want to look at these last two problems relative to that Arrhenius equation. Now these are kind of plug and chug type problems, work intensive, so get ready. In a series of experiments, the decomposition of nitrogen penoxide, dinitrogen penoxide, the rate constant was determined at two different temperatures. At 35 degrees Celsius, we have, say, K1 to equal 1.4 times 10 to the minus 4 seconds to the minus 1 at 35 degrees C. And then K2 was determined at 45 degrees to be 5.0 times 10 to the minus 4 reciprocal seconds at 45 degrees C. Now we need the Kelvin values on these just to be sure. This is 308. And of course that 10 degrees higher, 318 Kelvin. Oh. And what it's asking for, what is the activation energy for the reaction? And what is K3 equals what at 55 degrees C, which would be 328 Kelvin, right there. So this involves, of course, the Arrhenius equation, and then you take the expression and solve for delta EA and substitute and solve. So we have that, and so solving this for delta EA, let me move it down, I guess. So delta EA is equal to R ln K2 over K1, and that's going to be divided by this expression, which inverts and multiplies T2. All that's divided by T2 minus T1. So it's a matter of substituting and chug and plug. And so move up here and see if we can get. Now the R value is published typically in joules per mole Kelvin, 8.314 joules per mole Kelvin. But when you substitute into this expression, you need to be in kilojoules, because kilojoules per mole is the most common unit for energy numbers. So 0.08314, see, 1, 2, 3, I need another one. 0.008314 kilojoules per mole Kelvin is your R value. And delta E is going to come out in kilojoules per mole, so I'm going to delay putting all the units in because it just crowds stuff. And then K2 over K1, so K2 is 5 times 10 to the minus 4 over 1.4 times 10 to the minus 4. That's convenient because that will cancel out. And then T2, T1, T2, 308 Kelvin times 318 Kelvin. And then the differential between those two temperatures, 318 minus 308, that's 10 degrees. And it's all going to come out in kilojoules per mole when everything's said and done. 103.7 kilojoules per mole is activation energy. So with that, we can go back in here and solve for a K, rewrite the expression, Arrhenius equation, substitute a K3 in here, and then temperature 3, and solve for that one. Okay, so let's see, and that'll be 328 Kelvin. So we'll work rate constant is the topic at 328 Kelvin for the same reaction we're working with, and we just determined what the activation energy was, and we'll work off this one at 35 degrees Celsius, which is 308 Kelvin. Okay, and so we need K2 at 328 Kelvin. So we'll start with the Ln of K3 this time over K1. You could use K2 as easily. And delta EA over R again. And then it'd be T3 minus T1 over T1 times T3. So you get used to working with the equation. And like that. When we look at logarithmic ratios, this is actually Ln of K3 minus Ln of K1, and equals all of this stuff on the right. As such. Then we will add to both sides Ln of K1, and we'll have the Ln of K3, which is Ln of K1 now, plus delta EA over R, T3 minus T1 over T1 times T3. And so it's a plug and chug again. And when we get to the K3, get the numerical value over here, this K will then be equal to whatever that number is, e to the whatever power. And so, put this up, we'll make a little more space. Delta E is 103 point, oh, let's get the Ln. We got Ln of 1.4 times 10 to the minus 4, plus 103.7 over 0.8314, and 328 minus 308 divided by 308 times 328, like that. Okay, so now that we've got all the numbers in there, we'll just move it up. See if we can punch it out a little bit. Okay, so the computation here, if y'all back me up on it, if you would, I get 2.47. Working that out saves you some time. Then we simply take 1.4 10 to the minus 4 natural log, that's a minus 8.87. 7 plus 2.47, and we have a negative 6.4. And so when we solve for k now, out of k3, it's e to the minus 6.4. And so second e to the x, second scientific, that's 1.66 times 10 to the minus 3 seconds to the minus 1 is the outcome. So if you compare the K1, K2, K3 in here, you'll find that it's logical in as you heat the reaction rates go up, because K1 was equal to 1.4 times 10 to the minus 4 seconds to the minus 1. K2 is 5.0 times 10 to the minus 4 seconds to the minus 1. This was at 35 degrees C, and this one's at 45 degrees C. And as we've shown, K3 is 1.7 times 10 to the minus 3, minus 3, which is actually 17. Let's put it in that terms. 17 times 10 to the minus 4 seconds to the minus 1 at 55 degrees C. So we see a progressive increase in reaction rate. Well, what does that mean? That means there are more collisions. It's easier for the particles to find one another. They're zooming around looking for one another. If they're naturally reacting, they're probably high probability of the right orientations occurring. And so that's what it in essence means in terms of this trend of reaction rates. So the K value is the speedometer of a reaction. Even though we have rate laws and what have you, the K value is what people actually go for in defining rates of reaction. What's the rate constant? Anyway, so the transition state theory means that for a reaction to proceed, it must undergo all the reaction factors must undergo or must occur simultaneously at the activation energy. And this can be represented in terms of what we call a transition state diagram. For a given reaction, whatever. But you have to understand what it means in terms of endothermic, exothermic type reactions. So there's a special kind of notation that's used in representing thermochemical equations. Let's start with the exothermic reaction. We're talking about an exothermic reaction. That means energy is being liberated from the system into the surroundings. And so we'd have, say, reactants going to products. And one way to signify that is to add to the product side what we call heat of reaction. And that little circle up there means standard thermodynamic conditions. right there. Another way to do that is reactants going to products, semicolon, delta H of reaction is equal to a negative number, where the negative attached to the number, it indicates exothermic. Okay, so you have two ways to represent an exothermic reaction. If the numerical value is on the product side, or whether it's separated by a semicolon delta H reaction. Here's an example of that. Ammonia is produced by this reaction called the Oswald reaction. And you can write it as 91.8 kilojoules. So that's one way, and the fact that it's on the number is over here on the product side. And you don't put negatives in the equation, plus on the product side. Or you can write N2 plus 3H2 gas goes to 2NH3 gas, semicolon, delta H reaction is equal to a minus 91.8 kilojoules. So you put that negative into the expression, and that also indicates an exothermic reaction. Okay? I can go ahead and do the transition state curve, and then we'll do one for the endothermic. Okay, so I'm going to put this up here like this. The way that what the transition state curve shows is positional energy of the reactants and positional energy of the product along with the transition state energy. Okay, if you start, say, here is the reactant energy. This is energy, potential energy. I call it positional energy. Kinetic energy is energy of motion. Potential is stored energy. So the reactants have a certain amount of intrinsic energy in there. Well, in order for those reactants to make products, we have to heat them up to the activation energy. So that's showing an increase in energy to the delta EA, like we had on the Boltzmann probability curve. And then once you pass the activation energy, products are formed, and the products may be, if they're exothermic reaction, will be below the reactants. So this is your position of your product. So here's your product activated potential energy right here. And so you have energy of your products minus energy of your reactants, and that gives you what we call heat of reaction. So from this point to this point, delta E of reaction, which is the energy of the products minus energy of reactants, right here. Now, there are two other energy terms that you need to be aware of. The delta E for activation energy is the distance from here up to here, EA. This is where your activation complex occurs. It's a short-lived structure that decomposes either back into reactants or proceeds forward to products. But the distance is from the reactant energy to that transition activation complex energy is your forward activation energy of the forward reaction. And conversely, if we want to push the reaction back toward the reactant side, we would have a delta EA for the reverse reaction. And that would be the energy distance here. And notice the energy activation plus the energy of the reaction energy equals the reverse energy. It's the sum of these two, even though that's an exothermic reaction indicator in the reaction. If you were given the reaction energy and the forward activation energy and asked to determine the reverse energy, you don't subtract that. You add those two together because the distance, geometric distance, is what you need to take into account. Here's an example right here on your, right here, sketch a potential energy diagram for the following reaction. When it shows the reaction energy is 10 kilojoules, but it has a minus 200 kilojoule reaction energy. So you add those two together, so the reverse reaction is 210. I'll show you. So if we took that problem and drew a potential energy diagram for it, you need to know how to draw first, recognize in the problem that it's exothermic, and then draw, it doesn't have to be to scale, obviously. Draw something like this to begin that reaction. And so the activation energy for the forward reaction is a 10 kilojoules right there. But this, for the overall reaction energy, is 200 kilojoules. Right there. And if they ask you for the reverse reaction, you have to add those two together, and it's 210 kilojoules for the activation energy for the reverse reaction, if it's an exothermic reaction. Well, the next problem in there is an endothermic reaction. Now, when writing an endothermic reaction, it's just the reverse opposite of an exothermic. You put the energy number on the reactant side. So you have reactants plus the heat of reaction goes to products. Or you can separate it the same way, semicolon, delta H is equal to, but you use a positive value. But you don't have to put the symbology down, it's just understood to be positive. Whatever that number is on the end. An example would be H2O as a liquid plus 44 kilojoules would go to H2O as a gas or steam, like that. So that's an example of evaporation. Or you could put it in H2O as a liquid goes to H2O as a gas, semicolon, delta H of the reaction is equal to just 44 kilojoules, an endothermic reaction like that. Okay. So the example in our worksheet is sketch a potential energy diagram for this next reaction, and it's endothermic. As you look at the data, its forward reaction is 251 kilojoules, but it winds up at a 176 kilojoules. What's the activation energy for the reverse reaction? And label appropriately, you know. Okay. So we'll start out here, come up here, and then level off over here. So that's showing the product side at a point above the reactant. So that's energy of the positional energy of the reactants, and that's positional energy of the products. And so when you do the calculation for heat of reaction, you have a delta H of reaction right here on this side of that. You see you have this imaginary line going through the middle where you split the two. Well, your forward reaction energy is here now. But the heat of reaction is added to the reverse side this time over here. In this calculation. So in the problem that we have, we have 251 kilojoules for the forward reaction here. And the heat of reaction is 176 kilojoules. So to determine this one, you take heat of reaction plus the reverse heat activation energy equals the forward activation energy this time when you're working with an endothermic reaction. So delta EA forward is equal to delta EA reverse plus the delta E of the reaction, or delta H of the reaction. I should be putting in there delta H's. That's what is the proper symbology. You'll learn about that in thermo. Should be using H's in there. And so if they're looking for the heat delta H A for the reverse reaction, then that'd be delta H forward minus delta H of the reaction. And so that would, of course, be 251 minus 176. Everything comes out in kilojoules, and is endothermic. It'll come out with a plus value instead of a negative. All of the activations energy are positive. 251 plus minus 176. I get 75 kilojoules for the activation energy of that reverse reaction.